We just talked about impulse and momentum, and the next kind of like theory thing we want to do is to talk about what's called conservation of momentum. And this is an extremely important idea in physics. This idea of conservation of momentum. Almost all of physics revolves around conservation principles, and we've learned one of them that's called conservation of mechanical energy. We're about to learn the other one, momentum, and in a few weeks we'll learn the third one, which is conservation of angular momentum. Let's talk about this one first. So conservation of momentum. So this one basically comes from thinking about the following scenario. So let's say that I have two objects that are going to collide with each other, and a collision is just, I hope you know what a collision is, but like when a billiard ball hits another billiard ball, that's a collision. When a car crashes into another car, that's obviously a collision too. Those are the kind of things that we want to describe. And so suppose that I have a ball, and I call this one ball 1, and let's say that it moves initially with some velocity in this direction here, and we call that velocity just v1 initial. And this is where drawing these things is going to be... No, that's not what we're going to do. We're just going to call it v1 because there's a different way we can notate this. So it's moving to the right with some speed, right? And let's say that it's about to collide with the ball that's moving to the left with a speed... to the left. Okay, and this is going to be ball 2. And we'll say that ball 2 has a mass that we call m sub 2, and this has a mass that we call m sub 1. And that means that initially this ball has some momentum, p1, and we said momentum is found by just taking the mass of the ball times the velocity of the ball. And then this one's going to have some momentum that's going to point to the left, and that's going to be m2 times v2. Okay. Now they're going to hit each other, and upon collision, what's going to occur is that the balls are going to be, right next to each other, right? I'm going to draw these a little bit bigger. So one ball here, right? And then the other ball here. And they're going to collide, right? Now, when they collide, there's going to be some kind of a contact force right here, right? And there's going to be a force on ball 1 that we could say this is going to be the force of ball 2 on ball 1, and it's going to go that way. And there's going to be a force on the opposite ball as well. And we'll note that there's a force on ball 2 that points this way. And we could call that the force of ball 1 on ball 2, and that's also a vector. Oof, looks so bad. Sorry. I can leave enough for this is the force of ball 1 on 2, and it's a vector. Okay. Now, Newton's third law, right, tells us that those vectors are equal to each other, right? It says that if I take vector of the force of ball 2 on ball 1, that this should be equal to the negative of the force of ball 1 on ball 2, right? Now there's a third piece of this scenario that I'm going to draw here so we can use it to... After they collide, ball 1 is going to be moving this way, and ball 2 is going to be moving this way, right? So there's 2 and there's 1. And we're going to define their velocities now. The velocity of ball 1 we're going to call v1 prime, and the velocity of ball 2 we're going to call v2 prime. So this is going to represent the velocity after the collision. Okay, so this is like after. This would be like during. And then this up here would be before the collision occurs. And that's our scenario, basically, right? In addition to having these, velocities, that also means that this ball has a momentum that goes to the left as well. We can call that one P1 prime. And this one has a momentum that goes to the right. We can call that P2 prime. Now, we saw before that when a force acts on an object right here, so this force, right, it's going to have the effect of, it's going to change the momentum of ball 1. So F21 will change the momentum of ball 1. Oops. That force is going to have the effect of changing the momentum. The momentum was initially to the right, and now it's to the left, right? And I could draw the momentum vectors on here if I want to, right? So the momentum was this way for this one, and the momentum for this one was this way. But now they changed, right? So P1 was to the right, and now it's to the left. And that was as a result of that force right there, right? So we can say that F21, and I'm going to write this, I'm going to move these things like this. So we're going to say F21 plus F12 should be equal to 0, and then say that force, it's going to change the momentum of ball 1. So we saw before from our equation that that means that this is going to be equal to the change in the momentum of ball 1, right? Hope that made sense. Basically what we're saying from this expression right here, this tells us that F21 has to be equal to the change in the momentum of ball 1. Does that make sense? Okay. Plus, whoops, the same thing for the other ball, except this is going to represent, isn't it different units? Oh, yeah. I left something off here. Oh, no, I can't just keep erasing like that. That's not quite right, is it? Yeah. Sorry, it's equal to this. It's equal to the change in the momentum divided by the time interval, right? I'm so glad that you noticed that. So that's not, what I wrote is not quite right. This should be the change in the momentum divided by the time interval over which the collision occurs, right? Thank you, N8. Is it Nate? Is that what that's supposed to be? For figuring that out. Yeah, so it's going to change the momentum. You got to divide by the time. That's right. I'm often just skipping basic things. The force of ball 1 on ball 2, right? This one's going to have the effect of changing the momentum of ball 2. Right? And so this is equal to 0. But now what we can say is that they have the same time interval, so we can basically multiply both sides of this equation by delta t. And what we'll end up getting is basically that the change in the momentum of ball 1 plus the change in the momentum of ball 2 is equal to 0, right? But if the change is equal to 0, there's a better way to do this. I apologize. I'm going to start over because I don't want to. I'd rather do it the right way. Let's just no. Sorry about that. It's a better way to do this. Way better way to do this. Because we also have calculus. And calculus tells us that this is also equal to the derivative of the force, right? It's the derivative. So really, the better way to write this would be, this is the rate of change. Why didn't that switch over? Yeah. This is going to be the rate of change of the momentum of ball 1. And that's plus, this is the rate of change of the momentum of ball 2. There we go. Sorry about that. And these are both vectors, of course, too. Now, this equation can be written like this. We can write it as d dt of P1 plus P2. Right? Is equal to 0. And then, what does this equation say? If I take the time derivative of some quantity and it's equal to 0, what does that mean about the quantity inside of the... What does it mean about this? So if I take the time derivative of some quantity, this is the quantity, P1 plus P2, and it's equal to 0, then what does that mean about the quantity P1 plus P2? The momentum of ball 1 plus the momentum of ball 2. If the derivative with respect to time is equal to 0, what does that mean about these quantities here? Huh? They don't need to add to 0. They have to be constant. What Jesus said is right. If you take the derivative of something and it equals 0, then the quantity here must be a constant, right? So in this collision, that means that the momentum of ball 1 plus the momentum of ball 2 should be equal to a constant. And usually the way we end up writing this then is like this. We say, at any moment in time, the momentum has to be constant. The momentum of the system has to be constant. Another way to say that is that if we look at the momentum before the collision, that this should be equal to the momentum after the collision. And that's basically what conservation of momentum is. It's that you start off with some momentum, and whatever you start with, you have the same amount left over at the end, okay? So in this case, that would be something like this. If I take the momentum to begin with plus the momentum of ball 1 plus the momentum of ball 2 before the collision, that should be equal to the momentum of ball 1 after the collision plus the momentum of ball 2 after the collision. And they're vectors. We can write out what these things are. So the momentum of ball 1 is going to be the mass of ball 1 multiplied by its velocity before the collision, plus the momentum of ball 2 would be the mass of ball 2 times the velocity of ball 2. And this should be equal to m1 times the velocity after the collision, which we're calling v1 prime, plus m2 times the velocity 2 after the collision, which we call v2 prime. And that is our expression of conservation of momentum. Okay, drawing that line didn't really help. And there's a general statement we can make about all of this, which is this. Conservation of momentum states that when the net external force acting on a system that's a way of saying it. When the next net external force acting on the system is equal to 0, then the momentum of the system is constant. Or conserved, or whatever you want to say. We'll say conserved. It's a conserved quantity. It doesn't change, okay? That means that if you sum up all of the initial momentums in your system, that should be equal to the sum of all the momentum in the system after. It only works when the net external force is constant, because if the net external force is not constant, then you change the momentum of the system, right? That's what happened here. There was a change in momentum, right? There was a change in y momentum, there was a change in an x momentum, and it had the effect of changing the momentum of the object, right? Its momentum initially was mass times this, and its momentum after was mass times that. So you have a change because there was an external force. The external force was the force of the foot on the ball, right? In this system, where you have two objects that collide with each other, there is only an internal force that acts at the point of contact. And because it's an internal force to the system between the two balls, Newton's third law states that the force on one ball is equal to the force on the other ball. And if you know that the forces are equal, that means the change in momentums are going to be equivalent to each other. And as a result, you end up getting that the force is constant, okay? Now, another system in which we can describe momentum conservation like this would be a system like this. Suppose you have a flat surface, okay? And let's say you've got two people that are on, like, let's say, skateboards. So I've got one skateboard right here, and then I've got another skateboard right here, right? And there's two people here, okay? So there's going to be one person right here, and they need to have their hands here. There's one person here, their hands pushing this way, and then you've got another person on the other skateboard, okay? And their hands are pushing this way. I need to draw these hands a little bit longer. So they're basically like pushing off of each other, right? So basically what's going to happen here is that this guy is going to be pushed with a force by the purple person. So there's going to be a force this way. And there's going to be another force that's of the green on purple that's going to go this way. Okay. Equal and opposite, right? And there's other forces acting on the system though, right? This person is going to have some kind of a normal force, right? Call it maybe N1. And there's going to be a weight for this person too, which acts down this way. Maybe you call it W1. And the green person is going to have forces as well. There's going to be a normal force that acts up. Maybe we call it N sub 2. And there's going to be a force that acts down. And maybe we call it W sub 2. These weights don't have to be the same. Like this person could have a weight that's equal to like maybe 100 pounds. And weight 2 could be like 150 pounds. It doesn't matter. Okay? As long as the net external force acting on the system is 0. Like in this case, the net force in the y direction is going to be equal to 0. And that is to say that basically the normal force minus the weight, right, is equal to 0. And we can say the same thing for the other person. This is the net external force acting on it. This would be the net external force. Does that make sense? the net external force is 0. It doesn't mean that this force is 0 or this force is 0. Those have values, but they're going to be equal and opposite because it's two people pushing off of each other. In this system, momentum would be conserved, okay? The masses and the difference in weights will affect the velocities before and after the collision. If they push with equal forces, and this person weighs 100 pounds and this person weighs 150 pounds, which person is going to go faster? I'll ask that again because I asked it really quickly. So think about this. If this person weighs 100 pounds and this person weighs 150 pounds, and they push off of each other with an equal force, then which person is going to move away with a higher velocity or a higher acceleration, however you want to think about it? Is it going to be the smaller person or the larger person? Yeah, same force. The person that has less mass or less weight is going to be faster, right? But they will have equal momentums. Their momentas will be equal, right? One guy's going to go faster but has a smaller weight. The other person's going to go slower but has a bigger rate, right? So they're going to have equivalent momenta after the collision if they started off at rest, for example. Okay, does this make sense to you guys? Does this concept here make sense to you? You certainly probably heard it before. If you took a physics class, you definitely probably talked about conservation of momentum, right? And this is what it is. When the net external force acting on a system is 0, then the momentum of the system is conserved. And that happens in a lot of physical systems. For example, in Physics 1b, you learn about gases and the way that gases behave. And part of our understanding about what happens with them is that when they collide with each other, they exchange momentum. And usually the net external force is 0, and we describe that type of system, a bunch of gas molecules bouncing around in the room with conservation of momentum. A billiard table, like if you're playing pool, billiard balls, right? The way that billiard balls move is kind of governed by conservation of momentum, or geometry, or whatever you want to say. But at the end of the day, it's this concept that governs what's happening there. All right. So do you guys have any more questions, or have any questions about the general theory here before we look at some problems? I thought I made enough room and pull these things down a lot, but I don't think I did. So the first one I want to do is this one. Collision along a straight line. This is a very simple conservation of momentum idea. Do you guys have any general questions before we get started? All right, so let's look at a one-dimensional collision. This is about as simple as these kind of things can get. So we have two gliders with different masses move toward each other on a frictionless air track. After they collide, glider B has a final velocity of positive 2 meters per second. What is the final velocity of glider A? And then how do the changes in momentum and in velocity compare? Okay, so you've got all the information right here. I really hate their notation. VA1X. Do we really need 3 subscripts to describe one idea? I don't know. So we're probably going to just relabel these things here. We'll probably just call it VA. And we'll say that that's 2 meters per second. And we're going to have VB, which we're going to call negative 2 meters per second. We're going to have their masses, so you can see the masses right here. I don't need to relabel those, I hope. And we want to calculate what this quantity here is, VA. So we know VB, and we're going to say VB prime is going to be positive 2 meters per second. That's this one right here. And we're looking to find VA prime. What is the velocity of A after the collision? Okay. We're going to use momentum conservation. We're going to say that if we take the momentum of ball A plus the momentum of ball B, that should be equal to the momentum after the collision. And then we just plug in our values. So this is going to be MA times VA plus PB is going to be MB times VB. Everything's in one dimension here, so and this is going to be equal to MA VA prime plus MB VB prime. All right, so this allows us to solve for VA prime, and I don't really want to put numbers in, so we'll solve it out symbolically first. So it's going to be MA VA plus MB VB minus mb vb prime, all divided by ma. And this should be equal to va prime. And then we can plug in numbers. So ma was 0.5. VA was 2. Plus MB is 0.3. Multiplied by VB, which is negative 2. And then minus MB VB prime, so MB was 0.3. VB prime was positive 2. And we're dividing all of this by MA, which is 0.5. So 0.5 times 2 plus 0.3 times negative 2. We'll just do minus. So minus 0.3 times 2, and then minus 0.3 also times 2. Wait, really? Hold up. Negative 2, positive 2. Do these just completely cancel each other out? I guess they do. Sometimes they make these problems just way too simple in the textbook. That's the reason why we have the other example problems, but whatever. Yeah, so I guess these just cancel out, don't they? Am I crazy? No, they're both negative. They don't cancel out. Okay, I am crazy. Sorry about that. All right, so it's minus 0.3 times 2, minus 0.3 times 2. And then we divide all of that times 0.5, which is just like... No, not times 0.5. So it was negative. So it's 0.2 divided by 0.5. And then times negative 1. Where's the negative sign? I don't know. We'll just make it negative. So 0.4 is the answer. So VA prime ends up being negative 0.4. And then the unit should be meters per second. Does that work out right? I'm doing this on my calculator. So it's 0.5 times 2 minus 0.3 times 2 minus 0.3 times 2 divided by 0.5. Yeah, negative 0.4. That's the answer. Does anyone have any questions? Sorry, I got a little confusing there with the mathematics. That's part A. We also want to figure out how do the changes in momentum for the velocity, or for the velocity compare. How do the changes in momentum, let's take this one at a time. How do the changes in momentum compare? So the change in momentum for ball A, this would be basically PA prime minus PA. So this is going to be the mass of ball A multiplied by VA prime minus VA. So this is going to be 0.5 multiplied plus VA prime. This is VA prime, negative 0.4. Minus VA, which is 2. So 2.4, I think this is going to be 4.8 negative. Why don't you guys check that and make sure that's right? 0.4, this should be negative 2.4. Yep. And then for ball B, this is going to be PB prime minus PB. So that's PB is a mass of 0.3 kilograms, and we're multiplying that by the change. So the final velocity was 2 meters per second minus the initial velocity, which was negative 2 meters per second. So this is going to add up to 4, and then 4 times 0.3. What's 4 times 0.3 going to be then? 1.2? Yeah. It's positive in this case. Do you guys have any questions? Looks like someone's typing a question. Yeah. Yeah. That's right. I was like, this doesn't make sense. They should be the same. What's going on? Man, sorry about that. I was looking at this. 2.4, and I said times 0.5, and then I multiplied it by 2. So this is negative 1.2. Thank you very much, the physics innator. Thank you. Yeah, I was going to say, they need to be the same. I was like, what's wrong here? Okay, sorry about that. So the change in momentum for ball A is negative. The change in momentum for ball B is positive. And that's the way it's going to work always. During these collisions, the change in momentum have to be equal and opposite to each other. And that actually comes from one of our equations here. I think I erased it, but it would come from this equation here. This one tells us that you can effectively prove, and I was starting to do it, but the change in momentum for ball 1 plus the change in momentum for ball 2 has to be 0. And then that tells you that the change in momentum for one ball is equal to the opposite of the change in momentum for the other ball. That's what I was getting ready to write earlier, and then I started to realize that we could do it with derivatives because this is calculus class. But anyway, so there's your change in momentum. You can pretty easily see the change in speed, right? So the change in speed for ball B is just basically like, you know, final minus initial. So this is 4, and for this guy, the change in the velocity for ball A would be negative 0.4 minus 2, so this would be negative 2.4 meters per second. So the change in velocities are not the same. They shouldn't be, but consistent with what I said earlier, the ball that has the smaller mass has the biggest change in velocity, and the ball with the larger mass has a smaller change in velocity. Okay. So there we go. There's your answer. Does anyone have any questions? You know, I realize now that we could do some like demos with this using this FET website about how this stuff works. But I want to get into the two-dimensional stuff before we do that, because the two-dimensional stuff is where I think visualization is pretty key. I don't know if that's true. Maybe I do need to do this right now. So we have these FET, P-H-E-T. This website has a lot of really nice simulations for physics. And for bio and chemistry and all that kind of stuff. I don't know how good those ones are. I just know that the physics ones can be pretty good. In particular, there's this section on motion, and there's all these little things that you can use. I don't know if I showed any of these to you guys in class yet, but the one I want to look at is the one for collisions. And I don't see it immediately. There's two-dimensional motion, collision lab. This is the one we want to look at. Let's look at how, oh no, I think this is probably gonna work. No, it's blocked. Why is it blocked? Don't do this. Let's try it again. Okay, fine. So this allows us to kind of simulate these type of collisions, right? And in fact, if we want to, we could choose exactly the values we had in this problem. Like we can make one of the balls be 0.5, it already is. We can make one of the balls be 0.3. And then we can set up their velocities. So we do more data. I thought I could change the, oh, there's the velocity. So ball 1 has a velocity of 2 meters per second here. And then ball B had a velocity of -2. Positions don't really matter. Oh, whoops. Didn't mean to change that. -2. I want to just move the ball. I can do that, right? There we go. Okay, so we have one ball moving to the right. We have one ball moving to the left. They have equal and opposite velocities, so the velocity vectors are the same. And then we can click play. They'll collide, and then they'll bounce off like that. Get different velocity values here, probably because this collision is not an elastic collision. And I got to talk about what that means here in a second. So this doesn't exactly work for what we want to do, because now what's going to happen is we have to get it so that the velocity for ball 2 ends up being exactly, okay, I knew this was a little bit soon to be showing this. But, you know, this is, here. We can use this to show some features of how this works. So instead of trying to replicate the problem, we can do this. Let's start off with equal mass balls. So say both balls have a mass of 2 kilograms, right? What the conservation of momentum equation tells us is that if I start this ball off with some speed, and we're going to start with the speed of 1 meter per second, and it collides with this other ball over here, if it's what we call a perfectly elastic collision, okay, then what happens is that all of the energy from one ball gets transferred into the energy of the other ball, right? And so if we restart it, we see that ball 1 had a speed. Now I want to reset. I just want to make 1, 2, and 1, 2. And then I don't like the way it resets, but whatever. Notice that they collide, right? And then the velocity basically just goes over to the other object, right? This is what you would experience in a perfect situation where one ball has the same mass as the other ball, okay? Now, if we make it so that one ball has a different mass, so we make one ball like, let's say, half the mass, probably easier to make it double the mass. So if I make one 2 kilograms and I make one 4 kilograms, give this as a velocity, and we'll move it to the left here a little bit. I don't like that I have to 0. If I push play now, something different happens, right? If one ball has a smaller mass, ball 1, than the other ball, then the ball 1 basically ends up bouncing backwards, okay? You can make this even more extreme. We can make this ball have a mass of 5 times as much, right? And then this ball 1 is going to bounce pretty hard off of it now, right? Ball 2 carrying off some of the momentum. So these are all just examples of kind of simple collisions. If we make the ball that's starting off here bigger than the other ball, what do you think is going to happen if I do it like this? So I have ball 1 has a mass of 5 and ball 2 has a mass of 1. What's going to happen in this case? After ball 1 hits ball 2, is it going to rebound backwards or is it going to keep going forwards? What do you think? If it's going to keep going, yeah, exactly, that's right. And ball 1 goes off, ball 2 goes off much faster now too, right? They both experience the same change in momentum. So ball 1 slows down, it loses some fraction of its speed, but the momentum of the system basically remains constant. Now I haven't been showing these, but I don't know, I want momentum vectors. I don't know if that even shows it. It kind of does. The momentum vector basically like, yeah, I don't think it really shows it. What does the momentum diagram do? Oh, it's kind of nice, except it's going off the screen. Can I move this? That's the total. I can move these. That's the momentum of ball 1, and this is the momentum of ball 2. That's kind of nice. You can see that they add up to each other. So if you restart, and then you push play, do you see how it's kind of confusing because in this case, I'll do it like this. Let's try that. So there's the momentum of ball 1. It's that long vector. The total momentum is the same because ball 2 is at rest, right? And if I push play now, you see that basically some of the momentum, do you see that? Some of the momentum of ball 1 goes into ball 2, but the total doesn't change, right? The speeds are the things that you see, and the speeds change, but the momentums, they don't. The total momentum at least doesn't change, right? All right? We'll get into talking about what this elastic thing here means too, but I'm just kind of delaying that for now. Okay, do you guys have any questions about this? All right, we'll come back to this and we'll talk about elastic collisions now. We don't have to do elastic collisions yet. It's probably a good idea though. Like we can do these problems without talking about this, but we probably should. Let's do one more problem, and then we'll take a break. So this is the next problem we want to do. It's called the ballistic pendulum. If we, before I feel like I'm talking too much and not giving you guys enough time to think about this stuff. So, do you guys have any questions right now? So this is called the ballistic pendulum. This is a lab that if you took Physics 2A at the school, you probably did. We would have been doing a lab this semester with it, but unfortunately, I don't know. I might give you guys some data and have you do it. I don't know, but it just doesn't feel... I don't know. Okay, ballistic pendulum. A 10-gram bullet traveling horizontally strikes and embeds itself in a 990-gram block of wood. Okay, so let's label these things. Let's call this guy right here big M, and we're going to call this guy right here little m. And then say that for the values given in the problem, little m is 10 grams, and big M is 990 grams. Okay. The initial speed of the ball here is v initial. Okay. And I think the way I usually do this problem is I'm going to set a value for v naught. And we're going to say that the initial velocity in this case is going to be 100 meters per second. It's a bullet, so it should be moving pretty fast. That's actually probably slow for a bullet. In fact, let's make it a little bit more. Let's make it 300 meters per second. Okay. Find the rise in speed of the block just after the bullet. Find the speed of the block just after the bullet strikes it, the rise in height of the pendulum, and the fractional loss of kinetic energy. So the bullet moving to the right, it hits and embeds itself in the block, and then it rises up like this. So these are like 3 different moments. There's this moment here, and then there's this moment here. Right? So this is before the collision. This is after the collision. And then this is like after prime. This is after. Because there's a collision that occurs and then the block rises. Okay? We want to find the speed of the block just after the bullet strikes it. Okay? That's part A. A collision occurs, right? Between the before and after part, this is a collision. This is something that's really important to understand when you do problems like this. From here to here is a collision. Okay? During collisions, you can use conservation of momentum. So you can say that the initial momentum of your system should be equal to the final momentum of your system. The momentum of the system shouldn't change, basically. And for this, we have to sum up all of the momentum in the system. God, that looks awful. You have to sum up all of the momentum in the system. So this equation becomes, initially the block is not moving, so it has no momentum, but the little mass is. So your initial momentum in your system is going to be the mass of the bullet multiplied by the initial velocity. After the two stick together, then we say that the total mass of our system now is m plus m, and they're going to move with some common velocity, which is labeled as v right here, right? And we can even figure out what that is, right? But this is our conservation of momentum equation. This type of collision is often referred to as a perfectly inelastic collision. And this is a collision in which the two objects stick together. Why did I write that? After the collision. We call that a perfectly inelastic collision. And from this, we can solve for our velocity. So we can say the velocity in this case is just going to be equal to little m over little m plus big M multiplied by the initial speed. And that's going to be 10 divided by 1,000, right? M plus m is 1,000, right? 10 plus 990. And we multiply that by our initial speed, which was 300 meters per second. And this gives us 300 divided by 100, so 3, I think, right? That's their common velocity after the collision, is 3 meters per second. Okay. Part B says, find the rise in height of the pendulum. Okay. We're also going to find the angle, too, by the way. We're going to find the rise in height, but then we're going to find the angle. How would I find the rise in height of the pendulum? What do you guys think? What do I need to do to find the rise in height of the pendulum? Okay. What do you guys think? Yeah, conservation of energy, that's right. You're going to use conservation of energy. So going from here to here, we're going to use energy conservation. So this is going to be an energy conversion from here to here of kinetic energy into potential energy, right? So we're going to say, all right, for this, all we have to do is say the work done by non-conservative forces should be equal to the change in kinetic energy of my system plus the change in potential energy of the system. And there's no non-conservative forces acting, so this is going to be 0. This is going to be 1/2. Our mass is now m plus m, right? So this is the total mass multiplied by the change in speed. So this is going to be final velocity. Oops. What's the velocity here going to be? Well, this is where we're supposed to use our information about how the systems like this work. So first thing I'm going to do is say this is going to be y equal to 0. And we're going to start off by saying that, let me pick this, please. I guess it does. Ooh, whoops. No. Click that one. Oh, it's doing that thing again. Why is it doing that? Just let me click the green one. I'll click the green one. Do I need to do something like this? And then do something like this? Oh, I hate it when it does this. Okay, we'll switch to green then, I guess, since it really wants me to do it like this. So we're going to say at the bottom right here, we're going to define this point to be y equal to 0, and we're going to say our y1 is going to be equal to 0, and our v1 is going to just be the velocity v that we calculated. Up here, we're going to say y2 is the thing that we're solving for, what coordinate that it gets to, and we're going to say v2 is going to be 0 because, well, it's going to come to rest at that point. So now what we'll do is we'll say, here we're going to write v2 squared for change in kinetic energy minus v1 squared, and that's plus the mass of our system, which is m plus m, and then we go times g, and then we multiply by y2 minus y1. Some of these end up being 0. Why won't you let me, please? I just want to select a different color. Whatever. So a couple of these are 0. We said that y1 was 0, and we said that, v2 is 0. So our equation now becomes, the masses cancel as well. This cancels with this one. So we end up getting, what's left? We're finding y2, right? So y2 sorry, that's what's left, right? So that means that y sub 2 is equal to v squared divided by 2g. So that's going to be 3 meters per second. That's what we found in the first part for v, divided by 2 times 9.8. And this one is equal to, so that would be the rise and height of the pendulum. Does that make sense? Does anyone have any questions? Okay. So we also want to find the angle. This is just kind of a separate thing. Let's find out what the angle is. Let's talk about how we would do that. It worked that time. That's good. So we have this system, and it kind of goes up through this arc right here, right? I kind of want to just erase all this other stuff here for a second, just so I can show you guys on the picture what's going on. So now we have this object, and it rises through this kind of arc like this, right? If you look at the center of mass, it basically goes, and I could draw it from here to here. It goes like that along a curve. And what we just calculated right here was this distance, basically. That's what we would call y sub 2. You could also think of it as going along this curve if you want to, but it's not important. That's basically what we found, was the height, the change in height from here to here, right? And if I want to actually find out what that change in height is, what I can do is I can make a little triangle right here. A right triangle. God, that looks awful. I got to use a line for this. And the line's probably not going to connect where I want it to connect, but that's kind of okay, I guess. We can make a little right triangle like that, and then we can say define the chord length, which is 3 meters right here, right? So define the chord length to be L. So we're going to call L equal to 3 meters. Then L would be the distance from here to here. That's our chord length, right? But it's also this distance on this side. That's also L. So what we can say is that the other distance that we have here then is this distance from here to here. Okay? And I would say that that distance is equal to L times the cos of theta. And then I would say that basically y sub 2 should be equal to this distance here. And that y2 is going to be equal to L minus L cos theta. Can you guys see that? It's the total length minus the green piece. That gives you y2. So we can solve for theta then, because we know what y2 is here, right? What's the best way to do this? So if I say y2 is equal to L times 1 minus cosine theta, then we can isolate theta here by saying y2 divided by L, 1 minus this should be equal to cosine of theta. So if I take the cosine inverse of 1 minus, did I do that algebra right? y2 over L, and then add, subtract, yeah. So 1 minus y2, which was 0.46, divided by L, which is 3 meters. And that's going to be equal to the angle theta. So if we do that on our calculator, we'll have, so it's arc cosine of 1 minus 0.46 divided by 3. Try that again. 32 degrees. It was in radians. So you end up getting an angle that's equal to 32 degrees with the information that we have here. And I do this because sometimes they're going to ask for this, and sometimes they're going to ask for this. And I mean, so you guys are aware of, like, you know, what you would do to solve it, or have an example of how you might solve it. We have one last thing to do here, which is we need to find the fractional loss in kinetic energy. We'll do that. But do you guys have any questions? Okay. In that case, let's solve the last part of this. So part C now says... By the way, if any of you guys notice what I'm doing that makes it so I can't select the pins, just like let me know. So fractional loss of kinetic energy. This is something that when you're doing your homework, you're going to see questions like this pop up, and you need to understand what they mean by it. So fractional loss of kinetic energy. Let's just first calculate what the kinetic energies are, okay? So after the collision, the kinetic energy is going to be, and this is the energy loss from here to here. That's what we're looking at. This is what part C is going to be talking about, specifically going from this point to this point here. So kinetic energy at point 2 is going to be 1/2 m plus m. Sorry, I'm wrong. No, what I said is wrong. My bad. Sorry. There's no energy loss going from here to here. There's kinetic energy lost. Sorry, it's from this point to this point that we're doing part C, from here to here. So the kinetic energy at point 2, we'll call this, I guess, point 2, and we'll call this point 1. The kinetic energy at point 2 is going to be 1/2 m plus m times v squared, right? And the kinetic energy at point 1 is going to be just the mass of the ball times v initial squared. Right? Fractional loss of energy would be we take the kinetic energy at point 2 and we divide by the kinetic energy at point 1. That's going to give us the amount of kinetic energy that's been lost, or at least the fractional loss of kinetic energy. So if we take and plug these numbers in here, it's 1/2 m plus m times v squared. But v, right? Where was it? It's here. We're going to solve this symbolically. So v happens to be equal to m divided by m plus big M multiplied by v initial, and then we need to square that whole thing. Okay? So I'm plugging in that value for v here. And then it shows up here, and it's squared, right? We're dividing this by then 1/2 mass times v initial squared. And now we can do some cancellations right here. The v naughts are going to cancel because it's squared. This is going to cancel with one of these. The mass is going to cancel with the mass. The 1/2s obviously cancel as well. And now as I do all that stuff, I start to realize that it makes things a little complicated. What we're left over with, and you can do the mathematics for yourself to prove that this is true, is going to be you can do the algebra yourself if you want to. I think that's what you're going to get. Do you guys agree? I'll give you a second to like work out the algebra yourself if you want to. You guys follow the math? Do you have any questions? So the ratio of K2 over K1 is 1%. So the amount of energy that's been lost is 99% of the energy. It's not lost, though. It goes somewhere. The bullet has to burrow its way into the block, and that produces friction and thermal energy, temperature increase, that kind of thing. So that's where the energy goes. But it's an energy conversion then. This is common in these type of perfectly inelastic collisions, that the kinetic energy is not conserved, right? That's important to understand, because we can talk about systems in which kinetic energy is conserved or isn't conserved. But okay, does that make sense? Do you guys have any questions? Yeah, Ke converts to U, which I assume by U you mean thermal energy, maybe? Like the block and the bullet are going to heat up. It's going to burn its way into the or drill its way into the block. Okay, it's now almost 4 o'clock. It's amazing to me how fast these things feel like they go. What do we do? Well, okay, we did quite a bit, actually, didn't we? Okay. 4:10, I guess, is going to be when we start again. We'll take another 12-minute break and just say that we start again at 4:10. And I will stop the recording and upload it to YouTube.